All right, so let's talk about the new Ryzen 2000 series, the Ryzen 7 2700X, Ryzen 5 2600X. It's been a year now since the first release.
Over a year. It's March.
Okay, it's been a year and a month since the first release of the Ryzen parts, and you know, AMD is in the unfortunate situation where they delivered such an incredible increase in performance, IPC, raising expectation levels, all that kind of thing, that it's literally impossible to do it a second time around, especially considering that they were very upfront in talking about this being a fairly modest architectural shift, a fairly modest frequency bump. You know, they went from 14 nanometer down to 12 nanometer at Global Foundries, although there is a debate on what that even means. Right? Is there legitimately a huge difference in that process tech? Josh, what are your thoughts on that before we move on? Is there a real significant movement in that 14 to 12 plus or 12 nanometer, I guess, at GloFo?
Well, yes. But I mean, it's not obviously night and day.
Yeah.
I mean, if you look at it, you do get, you know, I think the primary push of this was efficiency, transistor switching performance, and not really optimizing for die size. So I think that overall the chips are supposedly about the same size as previous, but through your testing you can see that they are a little bit more power efficient and they do scale a little bit higher. And so you wouldn't get kind of one without the other. And so yeah, they can legitimately call it a 12 nanometer process. They can apply it to other products if people so desire, but it's an evolutionary step rather than something revolutionary, and it's not exactly the same as like TSMC with their 16 nanometer and what they have a 12 nanometer coming up. That there's going to be a significant difference in between their 16 and 12,
right?
Because their 16 was kind of based on their previous 20 nanometer work, except they're using FinFETs and a little bit different in the front end. But with this, it's more of the old time continual improvement that we used to see from AMD back in the early 2000s before they spun off Global Foundries.
Right.
This is, you know, they've taken a process. They've adjusted parts of it. They've done some smaller advanced features in others. And then another big part is, of course, just I think that AMD went through kind of with a fine-tooth comb and they optimized their Zen design.
Yeah.
So it all goes kind of hand in hand to get you this, not a significant jump, but it's an appreciable jump.
Moderate, I would say.
Yeah.
Jump. From a specification standpoint, what's interesting is, so first of all, I was going to say we talked about this last week, we didn't, because the pre-orders for this part went up on Friday after our podcast last week, right?
Friday the 13th.
Friday the
Usually
13th, of course. And then, of course, this Friday being 420, right? This is a very important, it's a very important week.
It is.
There is no 2800X. There's a 2700X that is now the new flagship part. You know, competing against that 1800X, kind of the 1700X, really. But then you get the 2600X versus 1600X. Now, what you'll see is the clock speeds are missing on the 1800X and the 1600X, but I did pull those up here. Basically what you get from the 1800X, the top end part then, to the 2700X top end part now, you get 300 megahertz. The max boost was 4 gigahertz before. It's now 4.3 gigahertz. On the 1600X, you go from 4 gigahertz to 4.2 gigahertz, and those are obviously the 6-core parts. Now, one thing worth noting right here is that the TDP does go up from the 1800X to the 2700X, from 95 watts to 105 watts. So even though you are getting 300 megahertz of additional frequency and 100 megahertz of base clock, it is coming at the expense of a little bit of extra power, although I think you'll see when you look at our review and other reviews that the performance per watt is still better on these solutions. The big architectural change that AMD claims are these latency improvements, and you can see on the slide here they talk about anywhere from 11 to 34% improvements in system DRAM, L1 cache, L2 cache, L3 cache, kind of equating to around 3% IPC improvement, with all else being equal between the previous architecture and Zen Plus. I asked many, many times and in many different ways for somebody to explain what they did to enable these cache improvements, latency improvements, and literally nobody had an answer for me that was anything other than, well, you know, things are better, and we took the time to really think about stuff and blah blah blah. Regardless, fine, sure, we move on. I'm sure everybody on the show will remember our ping testing that we did before that allowed us to really dive into and learn about the Zen architecture previously, in how, you know, inter CCX and intra CCX latencies kind of affected things and performance and all that. And this graph, a little bit complicated to understand, but it's interesting because we ran that same test on the new 2700X as well. And here we're comparing it to the 1800X. If you look at just the yellow and the gray lines, those are the ones where we set both processors at 3.6 gigahertz. They're both running a DDR4 2667. Which you'll notice is an interesting thing. If you look here, the green and yellow lines that are even, but the yellow line is what's important, is that the inside the CCX latency is actually longer or worse on the new 2700X.
Right. For those that don't understand what this is, inside the CCX is basically half of the CPU's cores if they're communicating with each other.
Yeah, the Zen design is built into CCX core complexes.
Yep. And there's two of them.
There's two of them on an 8-core part.
Yep.
And, you know, a 6-core part has 2 of them with 3 cores enabled on each. And each CCX has its own L3 cache that is shared amongst the cores, right? When you cross from one CCX to the other, even on the same die, you are crossing through Infinity Fabric, which is their name for the, you know, the basically the interconnect between all these components. And so what you notice in that green and yellow here is that inside the CCX, the latency actually got worse from about 50 nanoseconds to 55 nanoseconds or so. But if you look up here and you go across CCX, you'll notice that it got better. So from the gray line to the yellow line, we got about a 10 nanosecond improvement. And then we get about another 10 seconds if you bump up that memory speed from 2667 to 2933, which I point out because these new parts have a 2933 megahertz JEDEC spec official support, right? Whereas the previous gen stopped at 2667.
And then we just know that when you bump up the DRAM frequency, that the CCX communication
DRAM frequency is related to Infinity Fabric speed, and thus you see these improvements.
Right.
So it's interesting to me that they apparently had to have a trade-off in the architecture, whereas they wanted to improve the cross CCX communication speed. They had to sacrifice the inside CCX communication speed.
It seems odd to me because, like, there was all this discussion about the Windows scheduler and prioritizing and all these things.
It was all disproven, and they said that wasn't the case.
Where I'm going with that is as far as, like, that the scheduler would try to keep within a core complex first, and then only really go to the other.
Josh and I talked about this. You're saying why sacrifice the inside CCX performance?
Right, because you are going to get a benefit. Well, okay, so actually I can kind of see it. If you're a person that always runs in UMA mode, which is where...
You say UMA, but I really think it should pronounce Yuma. But that's
Yuma,
fine.
okay, whatever. It's not Numa.
Not Numa, yes, perfect.
What about Ms. Thurman?
Yeah, I know.
Uma Thurman.
But if you're running it not in NUMA mode, in other words, it's basically interleaving the DRAM banks across, then basically every time you go to hit RAM, you have to go across, across the fabric. Like every time
every other time.
Well, it's interleaved, yeah. As opposed to, it could potentially be everything was just on that side and local.
I think it's more simple than that. I think, and Josh and I had this conversation, Josh, correct me on this if I'm misrepresenting something you said. Okay. Is that the 10 nanosecond advantage you get at the top tier is worth more than the 5 nanoseconds you lose in the bottom tier. Like maybe there is another threshold of, hey, anything under 60 nanoseconds is actually doing what we want it to do.
Yeah, I can see that.
Right?
You're chopping off a bigger percentage across the Infinity Fabric than you're sacrificing within the core complex.
But Alan's right. You do kind of have to basically say, I believe that I'm going to have more applications that are using threads that are crossing the CCX more frequently than I am inside the CCX. But again, because nobody would answer my questions at AMD, I don't really know the answer here, even though I supplied them this data a few days ago.
Well, there's another significant thing there, which I'm not sure if we have charts to back that up or not. But like, if you can reduce the fabric related latency, you should also be reducing latency to the DRAM, just in general, from any core to the DRAM.
Correct.
Which is arguably, like, that's kind of important.
Maybe about 11% or so.
Yeah.
He says, pointing up at this graph that shows about 11%.
Another thing that we hadn't even considered is maybe some small kind of heuristic changes in how the front end of the CPU actually accesses memory. Maybe in your ping, it shows a little bit higher, but maybe it's able to stack up requests a little bit more efficiently to kind of send out to request this memory in L1, L2, L3, and main memory. And so maybe with just this ping, it looks like it's longer in the L1, L2, but in reality, maybe it's actually just faster. But we don't, again, you said, we don't know the mechanism
we don't know
that they're using to do this.
Other interesting things here, there is, even though we don't have the review finished yet, so the XForce, we are recording this before the launch, right? So the XForce 70 chipset, there's nothing new in the chipset itself.
USB 3.1 Gen 2.
Oh, is it really?
I believe so.
Okay. What you do get is motherboards that are, basically AMD learned a lot in the launch of the X370 in terms of power delivery to these processors and how to better work with the motherboard vendors to improve that. And so this gave the motherboard vendors a chance to re-release a new board with improvements in those areas. Support, make sure you have support for the 105 watt TDP, not just the 95 watt TDP. They add StoreMI capability, but again, it's not a chipset specific feature. It was supported on an X370. They're just kind of including it.
Yeah.
At like
it's like a licensed or cross licensed or something.
It's like the middle licensed version of what was it, Fuse Drive technology that we had talked about before. We haven't done a whole lot of testing on it yet,
right?
On it because AMD was kind of holding on to the final version until the very last minute. So we're going to dive some more into that.
There's supposed to be a bunch of changes coming, and so we don't want to spend a bunch of time testing it and then have to.
It also supports NVMe RAID.
Yes.
This time, which was something that they added to Threadripper that apparently they added to some X370 boards late in the game.
Yeah, it seems like it's kind of an option that comes over with the latest AGESA code because there have been a couple of X370 boards. I know one of the Gigabyte boards has NVMe RAID in the latest firmware, which added the newest AGESA code for the Pinnacle Ridge support.
Yeah.
So your mileage may vary on your motherboards. I don't know if you'll make it back to like B series chipsets or anything like that.
You might be able to go further back as long as you're not trying to boot from the RAID.
No, I'm pretty sure it would work.
Yeah, because that's
fine as long as you have the new UEFI.
Yeah. Well, I'm just saying, like,
supported.
If you want to be able to not just boot from it, but also be able to configure the array before you do your OS install, as an example.
Yeah.
Like that sort of thing. You need something in the BIOS that's there, like some sort of GUI to create the array. Otherwise, you have to jump through a bunch of hoops, and like you'd have to have a Windows install there to install everything and then create the array.
Sorry, this plane flying extremely low.
Yeah.
Any quick point on the NVMe RAID stuff from a performance standpoint?
They do, because of the way that they do it, they basically have a driver, they call it a bottom driver, that like it replaces the Windows inbox NVMe driver. So it's like a filter driver. It latches on to the NVMe devices, and then it makes them available to basically like a software RAID layer, right? And as you might imagine, that's kind of a lot of hoops to jump through, like kernel-wise and like driver-wise. And so it actually does take a hit on performance. We did some...
It takes a hit compared to...
I compared it to Z270 because that's what we had numbers available on.
It compared to an Intel...
Yeah, compared to an Intel RAID, but realize the Intel thing is much more of a packaged... It's part of the chipset. It's all like it's hardware support, right?
Which being part of the chipset is sort of a disadvantage because they're behind, not QPI. What's the...
DMI.
DMI, yes.
Yeah. So they are bandwidth limited, whereas they're direct CPU lane.
Yes. So if you're, the short version of it is if you're looking for straight line sequential transfers, then AMD is going to win.
Okay.
Right? Because you go more than one NVMe SSD and you've already saturated DMI on Intel. if you're trying to do an array, right? So sequential, it's great, even though the latencies take a slight hit, but for sequential, latency isn't that important. But as soon as you start getting into random access, it's like 30 to 50% longer latency on the AMD side. And that was using 960 Pro, which typically does like 60 microsecond latency, and it was going upwards of like 80 and 90 microseconds.
Sure.
If you take that in like a how much time was added standpoint, if you're a person that wants to use Optane SSDs to have really, really low latency, that's adding like more than 2x the latency of the product.
Okay.
Right? Because you're kind of throwing away. Optane does like 10 to 12 microseconds. If you add another 30 on top of that, that's really bad, right? So don't use Optane for a RAID here, but it's probably okay with something like 960 Pros or 960 Evos.
All right. I think we're going to do some more on that soon, because I would like to see kind of what those technological differences are. I know we've been talking about all this a lot, and we haven't touched anything on benchmarks. One last thing. All of these parts come with stock coolers, which I think people might just inherently write off because we've been so used to like the crud that is the Intel stock cooler. AMD's Ryzen parts had really good coolers, but this time they're actually, every part in the 2000 series comes with a cooler. The 2700X does, the 2600X, 2700, 2600, they all come with stock coolers. Different ones, like I think only the 2700X comes with the new Wraith Prism.
Yeah.
Is that right, Ken? This is your biggest, best 3-zone LED-enabled cooler.
Not this one, right?
Yeah, it's that one.
Oh, is it this one?
That one's got the RGBs.
Yeah.
Look at the switch.
And it also has kind of the different latching mechanism on it as well.
Yeah, it has a classic sort of AMD mounting mechanism, which is because, as Joshua would be likely to point out, this was originally an AM3 cooler, essentially. This was the original Wraith. It's been a little bit tweaked. They tweaked the design so you can fit in more RAM. They had the RGB stuff, but essentially is unchanged for the most part.
You did some testing, Ken, and like performance on it was really good.
Yeah. Like, at under sustained load with X264 encoding, it was like 2 or 3 degrees off our Corsair H110i 240 millimeter all-in-one water cooler.
Wow.
At stock frequencies.
Well, I mean, it's pretty stout, right? It's a copper block. Like,
it's direct contact.
Direct contact heat pipes, copper.
Talking about a 105 watt part, and the stock cooler is fantastic.
Yeah.
And that really shouldn't be overlooked, right? So this part's $329, but it comes with a cooler that may save you, I mean, even best case scenario, what's the cooler master? 30 bucks?
30, 40 bucks.
And the 8700K doesn't come with a cooler. And if it did, you wouldn't want to use it because those coolers were bad. Unless Intel changes their game up and stuff.
Yeah.
So that's another good advantage. So I want to look at a little bit of performance, and I'm just kind of jump around to some of the highlights here, some of the points that we know we're interested in talking about. This is actually an interesting one. So we look at single-threaded performance. Audacity MP3 encode. This is one we've used for a while for straight line, single thread. And you can see here that the 8700K is wildly faster. This is a lower is better result than the 2600X or the 2700X. This was an interesting one in that late in the game, AMD had worked with the guy who develops the lame plugin for Audacity. And apparently it was a 10-year-old compile or something like that.
Yeah, the version 3.99.3 is from November 2011, if I remember correctly.
So, long story short, they recompiled it with a modern compiler, set a flag for like SSE2.
Yeah, and it was x86 only before it wasn't compiled for x64.
And so this is the improvement now. So Intel's is still faster, but the difference drops from like a 30% jump
3%.
to like 3%.
You and those misleading graphs.
Yeah, we'll have to change that. We'll fix that. But hey,
it's the only one, Josh.
Good on them.
I'm sorry.
Good on AMD for like seeing that, going, oh, that's crappy, and engaging with a dev to make it.
And they're not cheating because they still lose. Like if they were cheating, they would make themselves win.
And we were talking about this before, like MP3 encoding. Yeah, who cares? I would bet the number of people who use Audacity for podcast editing is significant. It's a huge number.
Yeah.
It's GarageBand and then probably Audacity, if not the other way around. Handbrake.
Doesn't that sort of give you the warm and fuzzies of thinking back to Quake 2 and the 3D Now patch that Carmack developed for that?
Yes. Yeah, it does.
Fuzzies.
Memories.
The general performance outlook is that in multi-threaded workloads like Handbrake here, the 2700X is faster than the 8700K. In the X264 benchmark, the 2700X is faster. Cinebench.
The more important thing in the X264 benchmark is the 2700X to 8600K story. And I think it was past 2, maybe? It's like 50% faster. The Ryzen part is like 50% faster than the Intel.
28 to 36.
Yeah, because you have an additional 6 threads to run.
Oh, wait. The 2600X here is 2854 frames per second versus 22.
No, sorry, the other pass is the one I'm looking at. 100.51 versus 55.35.
100 versus 55. Yeah.
It was such a big difference that I ran that test again today on the 8600K to make sure I didn't screw up running the test.
Yeah. I mean, 6 cores, 6 threads versus 6 cores, 12 threads in a very well optimized algorithm that is highly threaded.
And that's one of the really common stories here is that the 2600X and the 8600K are much more fierce competition than the 2700X and the 8700K, and I think the 2600X comes out on top more often than the Intel part, except for really, really single-threaded workloads.
Right. Yes. Yeah. The highly single-threaded stuff's going to be a change there. So, we look at Blender here. There are improvements. The 2700X is faster, 2101 seconds versus 2400 seconds. But again, 2600X versus the 8600K, you're looking at like legitimately 1200 seconds of difference. This is a very long render, of course, but that's what's that, 20 minutes?
Yeah.
Or something like that, right? So those numbers mean a lot more in that case. So the story for Ryzen stays very similar. Single threaded, it's still behind, right? That didn't go away. It's a little bit better than it was because of the higher clock speeds.
And the faster memory.
And the faster memory up to 2933 out of the box. But in multi-threaded, it actually extends its lead. Again. So let's talk about gaming real fast. We're going to look at 1080p gaming. The story is improved here, but I would still put the statement out that the Ryzen 2000 series is still not as fast as an 8700K. It's close.
Yeah.
It's close.
It's getting closer.
Here's Ashes, right? 94.7 versus 103.7. Ghost Recon Wildlands, 104 to 113.
I mean, that's a reasonably close.
You're getting into the negligible gap. There are some games that show much higher. Like if you look at GTA right there, which is a very, very CPU heavy game.
CPU bound, yeah.
You see big differences, but
and in that case, like the 8600K is still faster than both of the new Ryzen parts.
Yeah,
for example. But they're not huge margins. Here's Assassin's Creed Origins, 85 versus 93.
Yeah, so you're running like 5 to 15%.
I don't think I ever saw 15%. I would say
GTA was just 15%.
And there's a couple of instances where the Ryzen is faster.
Yeah.
Right? Let's see. Total Warhammer is not one of them, but
one of the other interesting comparisons to look at is the 2700X versus the 7700K. They're pretty equal, if not the Ryzen part being a bit better in some tests.
Interesting. Yeah. Yeah, here's like 173 versus 175.
Yeah. So if you think of the 7700K as a really good 1080p gaming part, the 2700X is way more on par than 1800X.
Shadow of War is one of the ones where it's faster, 114 versus 111. So not a huge number, negligible within margin of error, but it's there, right? And then there's this instance where you see Forza, where the 8700K has a significant advantage, right? So I would classify 1080p gaming as tied to like 8% slower or so.
Yeah.
Right?
That seems reasonable.
And then when you look at, Ken did some testing at 1440 and 4K, that falls off, right? Obviously, the metrics are a lot closer. We've only got the 2700X and the 8700K here. And at 4K.
Obviously, the more you shift towards it being a GPU bottleneck, the more the CPU doesn't matter as much. And
so if you're on a widescreen monitor, if you're playing at 25 by 14, the differences don't really matter. We already talked about the
show the photo. Show the photo of the cool cooler.
Ooh.
Look at that. 3 RGB zones.
Ooh.
You got the AMD logo, you got the spinny fan part, and you got the ring.
Yeah.
Nice.
I'm spinning. Look at me.
We talked about the performance of it. It is very good. Power consumption. This was an interesting one. It's higher by like not an considerable amount, right? Like it's 20 watts higher than the 1800X, which is odd because it's only a 10 watt TDP difference.
Of course, TDP doesn't mean power consumption.
No, I know. But the 2600X is a more significant delta there. Like,
yeah, it's like
it's
more
30
like 30
something watts difference. And the 2600, you know, if you look at the 2700X versus that 8700K, it's using 40 watts more power.
Yeah.
At the wall. So that's, again, that's not insignificant. That's if we're looking at a mobile platform, that'd be a problem. Desktop platform, not nearly as big a deal. But if you want to talk about architectural efficiency and like design, clearly the Intel one is still more efficient because it wins in single threaded. It wins in gaming, but in multi-threaded, I don't know, what's the average kind of multi-threaded advantage that AMD has? Is it like 30% or something like that, like in Cinebench?
It's a little bit smaller than that. I'd say like 15 to 20.
So what does that turn into in terms of power consumption comparison? It's closer than that, right? So depending on what your workload is, that'll like take that into consideration.
If you have a cooler that can handle it, like the stock coolers in this case, like
then what's it matter?
Yeah.
No, I'm with you.
Maybe you buy a 50 watt bigger PSU just to have the headroom, but like
I think we've hit a wall on our idle power consumption, everybody. I don't know if anybody sees those blue bars here as we scroll down the thing.
It's going to take 40
We've hit the level of the 1080 Ti's idle power consumption, essentially.
It's maybe close to that. You did some real quick overclocking. We were able to hit, what, 4.3 on all cores?
4.2 locked on all cores, which is interesting because the single core turbo is 4.3, so you're actually losing 100 megahertz there with single threaded.
So there's two ways to overclock. In the BIOS, it's all cores, right, period.
Yeah.
If you use
At least
Ryzen,
in our BIOS, I don't know about other
that's
ones.
True. We were using the Asus board.
Yeah.
Right?
RG.
If you use Ryzen Master, you can do more. You can say it's single core, I want this to be able to go up to 4.5. But if I'm doing 4 cores, I want these to go up to 4.2, right? That type of thing. We didn't have a whole lot of luck with Ryzen Master. It was a little bit unstable. Didn't seem to apply settings.
And even locked at the 42x multiplier at 4.2 gigahertz all core running load, it was getting, I think, if you click on the screenshot, you can see, but I think it was like 87C on the H110. So it gets hot quick. There doesn't seem to be a lot of headroom here. It seems like
4.2 gigahertz. Okay.
It seems like they use the headroom up in kind of slotting out these products into the family.
Right.
Which isn't a bad thing.
Nope.
It means more people get more performance without having to mess with anything.
Right.
But if you're a hardcore overclocker, it doesn't seem like this is going to be your ideal part.
Jeremy's posted stories about 6 gigahertz or nearly 6 gigahertz on these parts using LN2. Clearly there is a bottleneck here on our water cooling / air cooling.
And let's be honest, you and I aren't very good at overclocking, and we didn't spend a whole lot of time with it. So obviously look towards other people who are into the overclocking thing. But
so let's look at the pricing. Go ahead.
So, I know you haven't gotten into this yet, but the thing that just strikes me the most is what the original 1800X was released at $499.
Yeah, $499.
$499.
It's $170 cheaper.
Yeah. I mean, it's impressive, right? A year ago, $499. Now you're getting better performance for $329.
Yeah, it's about 10% better performance.
Hey guys, this is what competition does.
Yeah, and you're getting a stock cooler,
and you get a cooler with it. I do think that's important, and for everybody who uses a Corsair water cooler or whatever other brand, or use custom loop, you don't care about that. But I bet for like what 80% of people, they're gonna love having this in the box. It's a good looking.
Mm-hmm.
It saves you $30, so it's essentially, if you think about it, you're getting it for $299 instead. Type of deal, whatever it is.
I mean, I have an i5-7500 in my computer at home, and I'm using a piece of crap Intel stock cooler still. Like it just
So this is it's a really interesting launch. You gave an editor's choice to the 2600X and a gold award for the 2700X. Why the distinction?
I think the 2600X is the sweet spot for a lot of users, whether you're even if you're a pure gamer. I think the compromises are a lot less than they were last year with Ryzen parts compared to Intel.
Yeah.
And comparing the 2600X, the i5-8600K, 2600X is just such better value. You get that multi-threaded performance. You get the extra 6 threads of multi-threaded performance. You get on par gaming.
Yeah.
And within 5 to 10%, maybe like within definitely very playable standards. And it's like $10 or $20 less expensive. You get a cooler in the box where you don't with the A600K.
Yeah.
You're gonna have cheaper platform options with AMD.
My takeaway from this, and I'm trying to wrap this up quicker because I know we're already running over our time, is that it's not a revolutionary step like the first gen was, but this is I think a little bit better than what we have seen from Intel in a couple of previous generations, where they did the tick tock thing or tick tock tock or
it's a waltz now or whatever.
Are you saying that we haven't seen much improvement since Skylake in 2014?
No, I mean that's not really fair to say. I don't know. I don't think this is necessarily better than those improvements, like gen to gen. It's probably pretty comparable. But what I would say is that's good news, right? Is that AMD was able to tweak process, tweak architecture just a little bit, get 200 or 300 megahertz extra performance out of it. Your price is lower, power consumption is a little bit higher, but overall a better solution for gamers. They're able to address some of those pain points, raise the memory speed, get those latencies down. I'm pretty impressed with what they've done. And
they're working on a pretty decent schedule of yearly. So we were one year and a month away from the initial one, and next year we're going to have a new process and a new design.
Yep.
That we can look forward to.
Yep. They've done well on execution. Okay. All right. That's going to wrap up our Ryzen discussion. Let's move on to the next topic.